All right, welcome back, everybody. Today we're going to be doing section 1.5, which is a bit of a review about graphing using transformations. So nothing about this section is particularly related to trigonometry itself. And we're going to look at the graphs of the trigonometric functions in detail in the next couple sections. So this one is kind of like a review of just general graphing techniques, I would say. So let me pull up the slides here and we'll get started. So this is section 1.5. So if you want to skim that section in the book, you can. But basically, we're just going to cover translations and then scaling and reflection. All right, so the nice thing about this section is that if you remember working with parabolas at all, maybe from high school or from another pre-calculus class or like a college algebra class, and you remember like moving parabolas and like stretching them vertically and horizontally and like shifting them around, you can use all of that knowledge that you have from that previous stuff to do and understand what we're talking about here and for the trig functions and for the trig functions. Yeah, so the same stuff that you learned for parabolas before applies to arbitrary functions, f, and we're going to look at that right now. Another note, we won't talk about these directly, at least not yet, but transformations can be expressed as compositions of functions. Compositions of functions. All right, but let's get started with the first type, translations. So translations are essentially shifts, vertical shifts or horizontal shifts. So let's say we start with a function f and we start with a constant c. C is a real number constant. And we're going to look at the function g of x, which is just f of x plus c. So what does g of x look like? This is just the graph of f of x shifted vertically by c units, whatever c is going to be. This is a good time to quickly review the function notation itself. Remember that this object here, f of x, that is the output of a function. That's what f of x is. It's the output of a function. So if you do f of x plus a number, what you're doing is you're taking the output and moving it up or down, depending on the value of c. So if c is positive, then the graph shifts upward. If c is negative, then the graph shifts downward. And if c is 0, the graph doesn't change, obviously, right? Because if c is 0, then you just have f of x, no change. But that's pretty much it. So if you add a number outside of the function value, so if you apply the function f, and then you add a value to that, that's going to correspond to a vertical translation, a vertical shift of some sort. Now let's look at horizontal shifts. So horizontal translations, same kind of a setup. We're going to start with a function f. We're going to start with a fixed constant c, that's a real number c. And we're going to look at the function that you get when you take your input and subtract c from the input. So what does this do? This gives you a horizontal shift of the graph by c units, depending on the sign of c. One thing I'll mention is this. So a lot of students point out that uh, we're doing a minus c. And what I try to do is I try to explain it here. The reason that this works the way that it does is because you're changing the input of the function. So let me emphasize this right here, right? So we're changing the input before we apply the rule f to that input. So that's why this results in a horizontal shift. Usually we will plot inputs on the x-axis or the horizontal axis, and we'll plot outputs on the vertical axis. So here, if we change the input before we apply the function, you're basically shifting along the x-axis. But what I highlighted here is kind of why the sign appears different, because it's like a negative c, or it's like the opposite of c here. What this is saying is that the value of g at x will be the same as the value of f at x minus c. So in some senses, it's kind of like you're not so much pulling the graph left or right, you're pulling the coordinate axes themselves left or right, and then evaluating the function. But if c is positive, this shifts the graph to the right. So if you had f of x minus 2, you would shift the graph 2 units to the right. Then if you had a negative c, that'll shift you to the left. So if C was like -5 or something, that's going to shift you to the left instead. And then if C is 0, there's no change, right? No change there. Okay, so here's just a general picture of what all these different types of translations look like. You've got your original function f of x right here. You shift it up by a value c, you shift it down by a value c, you can shift it to the right by a value c, and you can shift it to the left by a value of c, just like so. So that's really what we're looking at. And by adding c to the input or adding c to the output, that gives you horizontal or vertical shifts. Okay, so that's pretty much it for translations. We'll explore the sine function and the cosine function in the next section. But now let's take a look at vertical scaling and reflecting. So the setup is the same as before. We're going to start with a function f and a constant c, a real number c. And now we're going to look at what happens when we take f and multiply the outputs by c. So once again, remember that this symbol f of x, that's the output of a function. So that's like the height, you could say, of the function. And we're going to take that height and multiply it by some number c. Okay, so what does this do? Well, if I have something that has a certain height and then I multiply it by c, it's going to scale that value by whatever the value of c is, right? So this is just a vertical scaling by a factor of c. Another note, if c is negative, then that takes the entire graph of f of x and flips it about the x-axis, And that makes sense if you think about it, right? Because if I've got my function f and I've got my outputs f of x here, well, those outputs appear somewhere on the y-axis. But then if I take that output and I multiply it by a negative number, it's going to take it and flip it. It's going to make it the opposite of what it was. So if I were up here, I would now end up down here below the x-axis and vice versa, right? So if I was down here and I multiply by -1, I'll flip up instead. So negative values of c correspond to a flip around the x-axis. And I say it down here too. Indeed, if you look at the function negative f of x, that's just the reflection, a vertical reflection of the graph. Okay, more details. Still with the same setup, this value c. If the size of c is bigger than 1, you're going to get a vertical stretch. Why does that make sense? Well, if I've got my outputs f of x, and I multiply those outputs by a number that's bigger than 1, or whose size is bigger than 1, it's going to take those outputs and stretch them vertically, right? Because now we're going to have not just one of them, we're going to have more than one. So if f of x was like 2 and c was like 3, well, now I'm going to have 6, right? Because 3 times 2 is 6. It's going to stretch everything vertically. Now, compare that to if the size of c is between 0 and 1, then what you get is a vertical compression. This makes sense because if you think about the outputs, f of x, if I multiply those outputs by a number that's between 0 and 1, I'm getting like a smaller fraction of that number, like a smaller amount. So what happens is everything gets squished. That's a vertical compression. If c is 0, then our function is 0. If c is 1, the graph is unchanged. And if c is -1, it's flipped around the x-axis, like we were just saying. All right, now let's look at horizontal scaling and reflection. So same setup again. Start with the function f, some real number c. But now what we're going to do is we're going to multiply the input by c. We're going to multiply the input by c. And what does this do? Well, if we multiply the input, it's going to squish or stretch horizontally, right? Because inputs are on the x-axis. So if we start multiplying them, it's going to have this effect. It's going to squish or expand horizontally. There you go, by a factor of c. Similar behavior here. If c is negative, then it flips your graph around the y-axis. And that also makes sense if you think about it, because if like the origin is here where my pencil is, here, hold on a sec. Let me go back to the camera here. Yeah, okay, so if my origin is like this pen, this Apple Pencil here, and I've got a value that's over here, and I multiply it by -1, it's going to go over here. So it's quite literally a reflection. It'll be the same distance away, but it'll be on the opposite side. That's what's going on. Okay. Yeah, back to the slides. Yeah, and that's just what I said down here too. So if you change the sign of the input, you're basically flipping horizontally. Now, uh, some details to point out here. So the compression versus stretching behavior is actually switched for horizontal compression and stretching, and I'll explain why in just a minute here. But if the size of C is greater than 1, then that's actually going to give you a horizontal compression, a horizontal compression. So if this number here, if I multiply the input by some value C where the value is bigger than 1, then that's going to cause my graph to shrink horizontally. It's going to like squish it, like so, compress it horizontally. The reason is this, the reason is actually easier to see, I feel like, with the sine graphs. But if I multiply by a number whose size is bigger than 1, then it's kind of like I'm going through the inputs faster than normal time. That's the way that I like to think about it. So if C is 2, well, what I'm saying is go through the inputs twice as fast as before. If C is 3, it's saying go through the inputs 3 times as fast. And if C is bigger, 4 times as fast, 5 times as fast, 10 times as fast. And so what this does is it produces your graph a lot more quickly, right? It produces the look of the graph, but in a shorter amount of space because everything's basically being squished horizontally. Now compare that to the other scenario. If the size of C is between 0 and 1, then you're going to get a horizontal stretch. So if C was like 1/2, so if C is like 1/2 instead, then what you're doing is you're getting a horizontal stretch. And the intuition for that is basically the example that I just gave. If C is like 1/2, then what I'm saying is go through the inputs half as fast as normal. So instead of going through the graph like it normally would, now it's going to go like a lot more slowly, half as fast, basically. So that number C is kind of talking about speed. And as we'll see with the trigonometric graphs, it's affecting the period of the graph. But we'll see that in the next section. Some other cases, if C is 0, then f of 0 is f of 0. If C is 1, the graph is unchanged. If C is -1, you're flipping around the y-axis, just like I had pointed out before. Okay, here's just a general overview of all those squishes and stretches. So here's the original function f, and then if you stretch it vertically, you get something that looks like that. If you compress it vertically, you get something that looks like that. Here it's flipped over the x-axis, and then here it's flipped over the y-axis. And that's why the input over here is now negative instead. All right, so that's the basic idea. If you want, you can follow this Desmos link right here, and this will actually take you to a sine graph where you can play around with it and mess with it. But we're going to do that in the next section instead. So if you want to look at it now, you can, or you can wait until the next section. But that's pretty much it. That's pretty much it. So let's play. Try to do the homework on this section, get some review. And then, yeah, we'll get a lot more details about the trigonometric functions and their graphs in the next section. But that's it for this lesson. So thanks for listening again. I'm glad it was a short one for a change, and I'll see you next time.